Hi everyone, and welcome to video number 9 of this series, in which we are learning how to model an end plate steel connection, which is this model that you see here. And well, now we are going to finally run this model, which means that we are going to solve the mathematical model that we have defined using the finite element method, and Abaqus is going to do this for us. Before we put this model to run, we need to finish the setup of this mathematical model because it's not completely finished yet. Let's see, before we start working on it, let's just set up some things. First of all, in the draw mode, this button here, select PID. And let's select here the Abaqus deck so that the structure of the database is the same as I have here. And also in the database, deactivate visibility of curve and point. And in the yellow buttons, let me activate visualization of double clone. Make sure that you have everything that I have activated here. And in point, deactivate spots. And that's it. Well, we don't need to upload the quality criteria file because we're not going to make any modifications in the mesh. Okay, so let's see what we need to do here. The best way to know what we need to do in our mathematical model is to look at the step manager so that we can see what are the steps that we have defined and what we have defined in each step. So in the step item in the database, maximize it to see the other items inside this group, and then double click on step manager, and then double click here on this item. And then this is going to this window is going to show up, and then in here we can have access to the steps defined in this analysis. We have 2 steps, and then we can expand each one of these steps to see what we have inside. Let me increase the length of this column, and then you see we also have this one, which is step 0 in Abaqus, or the initial step. In this one, we have the definition of the contact, this contact right here. And we have this boundary condition, this one, that fixes all degrees of freedom here and here. In the first step of the analysis, we have the connector load. So here we have the bolt pretension. And then this boundary condition that we define here is propagated to this step. So we don't need to redefine it here. And then on step 2, we have, if we double click here on step 2, remember that we have resetted connector load because we're going to replace the connector load and use a connector motion, this one, that fixes the first degree of freedom. So the relative position between the nodes that are part of the translator connector are going to be kept as constant from the second step until the end of the analysis. And then we have this boundary here, which is this boundary condition that we have established. If we double click on it, here we have minus 200 millimeters in the downward direction. Let's just adjust one thing here, guys, because you see, a double click on step 2, and then in parameters, you see that we are applying an initial increment of 10%. And we have this displacement of 200 millimeters. 10% of it is 20 millimeters, which is a lot. So I guess that's a good number. Let me open up an Excel spreadsheet. And I guess that's a good number is maybe 1 millimeter. And 1 millimeter divided by 200 is this in percentage. So let me define this as the first increment. Okay, so here we have 0.5%, less than 1%. We're going to start this as the initial increment, and then Abaqus is going to decide the next increment. Okay, it's good to have this maximum increment here because we are going to extract a moment versus rotation curve, which is this curve that we see here, moment versus rotation. So we need many points to be plotted so that we generate a good looking curve. So it's good. It's a good practice to establish a limit of increment that we can have. All right. Now let me click on OK, and let me go to the first step. Double click here, output requests, and then first of all, let me adjust one thing here. Obviously, that before recording this class, I have tested this model, and I noticed that there are some things that we need to adjust here. The contact output, double click here, and then in here in identifying keys, I noticed that there are some outputs here that are not compatible with this type of analysis, which is okay. Total area in contact and total forces due to contact pressure is not compatible with the way that we set up this model. But we can calculate contact displacement, C status, and which is contact status, and contact stresses. This one is actually the most important one, contact stresses. This is the one that I actually use most of the time. Click on OK, and then we need to update. Now click on, while you have this selected, click on update, and now we have this updated. Okay, well, you would find this out when you try to run the model, and then you're going to get an error, and then we would have to adjust it. So just to save some time, I'm doing this right now. Okay. All right, now we need to do one thing here. Click on OK, close. We need to somehow measure the rotation that we have occurring in the end plate connection, because we need to extract a curve like this, right? Moment versus rotation. The moment calculation is going to be easy to calculate, because imagine that I have a displacement applied here in the downward direction. We know that a displacement is a prescribed, actually a prescribed displacement boundary condition generates a reaction force. So we know that when the software calculates the active displacement, it removes from the set of algebraic equations the ones that are related to the constrained displacements that has the reaction forces. And then, well, after the software calculates the active displacements, we can use this result to put in the constraint equations that has the reaction forces, and then we can calculate the reaction force. Well, in a nutshell, we are going to be able to calculate the force that we have acting in the downward direction at this node. And we know that the distance between this node and this region is 1200 millimeters, right? We can use the measure tool, zoom in here, select this node, and then we can select one node that is part of this phase here, and then store, and then we are going to have the this distance here in the x components of this distance is equal to 1200 millimeters. So we just need to calculate this force and multiply it by the distance, and then we are going to have the moment, right? Now, how do we calculate the rotation, right? You see that we have these plots here that has this rotation, and then there is also these other plots here that has this other kind of rotation. In these documents, we have a definition of how this is measured, this kind of rotation. But the one that we're going to plot in this study is this one here, phi without the superscript s. Let me see if we have this this definition here. So the rotation phi is the total joint rotation of the beam to column and plate connection, while phi s is the shearing rotation, which is part of the total rotation contributed to by the shearing deformation of the column panel zone. So this one is a little more complicated to calculate, phi s. What we're going to calculate is the total rotation. And to do this, I guess that's the most practical manner. Let me see one thing here. Yeah, I guess we don't have any images here, maybe in the beginning, or maybe in this other document that we have that has experimental data. I remember that we had some drawings here that, yeah, I have this drawing here. You see, we have phi, which is the total rotation. So it's measured as the angle between this horizontal line and this inclined line that follows the inclination of the plate. So this is what I want to measure. Okay, so let's go back to the model, and to measure it, it's going to be pretty easy actually. Let me get a view like this, and by the way, to get views like this, you can use F1, F2, F3, and etc., and then you're going to get one kind of view for each one of these shortcuts. Let me deactivate the visualization of measure in the database, uncheck this box, press F3, and then when I apply this force in the downward direction, actually I apply a displacement, but this generates a force. This joint is going to rotate. So you can imagine that if I get one node here in this region, for example, that is part of the plate, and if I measure the rotation that this node undergoes, then I'm going to end up measuring the rotation of this whole connection. Okay, it's like I'm getting a node that is here, and then I'm measuring the rotation that this node undergoes, and then I'm going to end up measuring this rotation. Okay, well, it's not a good, you see that it's a good idea to get a node here, but if I get a node here, for example, maybe this is not a good idea because we have this happening here in this region. So I should get a node in this region here in the middle of the beam, which is here. Okay, well, just to be sure that you're going to get kind of the same node, because obviously that you don't have the same mesh as I have, but just to get approximately the same node, go to the classic topo module, and then in the points group, select on COG, left click and hold, and then select points. Zoom in here, select this point here in the corner, and then this one, middle mouse button, activate the visualization of points here in the database. And now we have the point here right in the middle. Let's go back to the classic mesh module, and then here we have this point here. In my case, I have a node in this position already. But it's okay if you don't have a node in this position. You can get any node near to this point that we have created. So we are going to create a set. Go to set list, right click, new, and then I want to select node. In the selection mode, I want to select by entity. Make sure that you have the same symbol here. If not, you should click here. And then zoom in here and select these nodes that you have positioned near to the point that you have created, middle mouse button, and then this is a node set, and this is going to be the node that I'm going to use to measure rotation. I'm going to name it as measure rotation, and then click on OK. Now let's go to the step manager again, and then double click on step 1 where we have the output request defined. And now I'm going to define a history kind output request. What we have defined here is a field output request so far, right? To define a history output request, I need to create a new line, output, and then define here as history. And then in the frequency, I'm going to set it as 1. So it's going to calculate this every increment that we have. And then I'm going to insert. Now we have this new line, which means that everything that we define below this is going to be a history output. So this is how it works. You see, here we have a field output, and everything that is defined below is going to be a field output. A field output is a kind of output that measures something in a large group of entities. So for example, for all nodes, for all elements, for all connectors, and etc. Now, a history output request is one that we need to select a set of a limited, a certain quantity of entities to measure something. In this case, we're going to measure rotation for one single node. So in here, let's select node output. And then in here, we need to select that node set that we have created. Use the question mark while you have this field selected to see a list of sets. Scroll down and find the measure rotation set, double click. And now we have the ID of this set selected here. And now in here, we can select if we want to measure using the global coordinate system or not. Since we don't have any, this node is not assigned to any other coordinate system, because this is something that we can do. We can have a coordinate system defined for a specific node. But in this case, we don't have any coordinate system defined. So it doesn't really matter if I choose global here or not, because it's going to be measured in the global coordinate system, which is this one that you see here. Click on identifying keys and then search for U, expand U, and then I want to get rotations. Okay. And then the software is going to calculate rotation about X, rotation about Y, and rotation about Z. But what really matters is rotation about Y. As you can see here, we want to measure rotation about Y for this node. Click on OK and click on Insert. And then we have this new line below the history output request. So this means that this is a history output request. All right, so I guess that's it that we need to define. Click on OK. Guys, be sure that you have this checked so that these two steps are active. And that means that when we output the .inp file, this is going to be written in that file. Let me think here about if there is anything. Okay, yeah, there is one thing. We need to create gravity, right? Even though this is not going to really impact so much in the results, because the load that we are going to have here is very, very large, and the body force gravity is not going to really make so much difference in the final results. But let's apply gravity so that you learn how to do this. Let's go to the Abaqus deck, and then inside loads group, we have deload. Left click and hold, and then while you have the left mouse button clicked. So you're holding the left mouse button, select gravity, new, and then now you can release the left mouse button. And then I'm going to define gravity in, let me think here, maybe in the first step. Yeah, while I'm applying the bolt pretension, I'm going to also apply gravity. So in the first step, in the negative z direction. So you see, in here we have comp 1, comp 2, comp 3. We need to define a unit vector to define the direction of gravity. I want it to act in the negative z direction, so I need to define 0, 0, minus 1. The magnitude is 9, 8, 10. So in here we need to define gravity as millimeters per squared second, because length here is millimeters. We have defined these as millimeters, right? And gravity is equal to 9,810 millimeters per squared second. Okay, this is just a standard value for gravity. Obviously that this varies depending on the part of the world that you are, but usually this is the value that is used. And then we can click on OK. And then you see that we can expand the load group. And we have this new item, deload gravity, select, and then you see that this is a body force, so it's acting on the whole volume of this domain. Okay. All right. The next thing that we need to do is go to material list, and then you see that we have these 3 materials, right? And we have this column here defined. And it's not checked, which means that when we output the .inp file, this is not going to be written in that file. So we need to check this. I don't know why ANSA does that, because whenever you create a new material, it's not automatically defined. If you can't see this column, click here in this item and then write define. And then you're going to find these and then check this box. In my case, it's already checked, so that's why I can see this column. Close this. Well, I guess we are almost finished. Or we are finished. Maybe we are finished. Okay, let's try to run it. I know that we're going to face one issue here, because as I mentioned, I have tried to run it. And well, I'm going to run it even with this issue, just for you to see what happens when we have an issue with the module, how we can debug it, and etc. So here I have the working folder that I'm using. I have the .ansa file here, right? And then I'm going to use this folder to place my .inp file. I'm going to copy the path to this folder. I'm going to go back to my ANSA session. And then in here, oh yeah, there is one thing that we need to do. I just remembered. Every time we finish creating a model, a good practice is to use a function here that is named as compress. You're going to find it in the yellow tools that we have here above. In my case, I need to click here to see more options. And then here we have it. Again, if you don't find it, you can search this function here. So click here, compress. And then in here, basically what this tool does is to delete every entity that is not being used. And then this is a good practice, because sometimes we have some nodes floating that are not connected to anything. That is going to yield to errors when we try to run this model. Okay, but anyways, we can have materials that are not used. Then the software can delete it because it's not being used. it's a good practice. So first of all, click here to see details of what is going to be deleted. And also click here in all decks, because I want to delete entities from all kinds of solvers. Even though I have defined only Abaqus related entities, I usually select all decks here because sometimes I receive a module from another person that was built for Nastran, and then I have translated this module to Abaqus, for example, but I yet have some Nastran entities that I need to compress and delete. Okay, so I usually select all decks here. And then in here, you see that I have some things checked. Actually, I have everything checked. But you see that in here, you don't have this checked. So to make sure that everything is checked, I'm going to click here to uncheck everything. And then I'm going to click here to check everything again. So I'm going to scroll down. And then you see that everything is checked. Now we have the geometry group. Everything is checked as well. Now, let me scroll up. And then you see that, for example, I have one Ectron material. Ectron is a solver that is going to be deleted because it's not being used. Looks like we have a boundary condition set that is not being used. ANSA's material. I don't know what is this material. Let me see here. Yeah, I don't know why, but it's going to delete. I don't know, because these materials that we have defined here are all being used, but for other solver decks there is an unused material. So that's why it's important to use the compress tool. But we should always check what is being deleted, because sometimes it's going to delete something that we don't want to be deleted. Okay, but looks like here we have only this material that is going to be deleted. And in geometry, 16 faces. Let me double click here to check what are these faces. Well, I don't know what is these faces, but looks like it's nothing important. Let's click on OK. Now you see that in this region of the screen, we have the information of what has been deleted. I was just worried about these faces, but looks like we have all faces that we need here. Nothing important was deleted. Okay, so another thing that we need to do before exporting it is to run a check. So in the green tools, find this button here, checks. If you don't find it here, maybe you're going to find it here. And then we have the checks manager. Actually, you see that we have many checks that we can run. But in the checks manager, when we click on it, this opens, and then we have this option here, Abaqus checks. Double click on it, expand this, and then you're going to see that we have a list of checks that are going to be run. And well, we could access each one of these checks manually by clicking here and then going selecting each one of these items isolatedly. But in here we have a group of checks that ANSA separated that are suitable for Abaqus, that are a good choice for Abaqus. Now we can execute on all entities, as you see here, and we can click on, you see that everything is checked here, right? When we click on execute, each one of these checks are going to be run on all entities. And now it's finished running. And then you see that in status, when we have this symbol, it means that everything is okay. So this first one is for duplicate. If we select it, you see that this checks reports elements with identical nodes. So we don't have any duplicated elements, which is good. This is something for geometry. This is for massless. You see that we have this symbol, which means that we have warnings. If we double click here, it's going to show more information. I'm going to select everything from this list, and I should have this activated. so that it's going to be highlighted in the viewport. And then I see that it's related to this node here that is connected to a translator. It's saying that this node is massless. There is no mass assigned to it. For a static analysis, which is this case, this is not a problem. But for example, if I want to run an explicit dynamic analysis, I know that this is an issue. For this kind of analysis, I even have a script that I have written, a Python script that I can run, and this script identifies massless nodes and creates a very small mass, so that it's not going to be a massless node anymore, but the mass is very small, so it's not going to impact in the final mass of the structure. Anyways, this is not something that we need to care about in this course, because this is not an issue for a static analysis. So we can ignore these warnings. Here we have just this error that was found for contact. Double click on it to see more information. We have this item we can expand. Clicking here, we have this error. Let's increase this and expand. Double click here to expand these. And then we have penetrations in PID 3 and PID 4. So he's saying that there is penetration occurring in this contact definition. And the reason for that is because these two, let me close this. And by the way, before I close this, you see that if I right click here, I have this option fix. So there is like an auto fix option that sometimes is worth it, but sometimes the software is going to modify some things that you don't want. In this case, let's not do this. Let's close. By the way, if I go back, you see that this is the only error that you have, that we have. We don't have any other errors. Okay. So let me close here. Let's go. Let's click here in quality criteria, presentation parameters, activate visualization of draw shell as solid, apply, and then you see that these two faces are very near to each other. We have created these two faces in a way that the distance is going to be exactly equal to 20 millimeters. And the thickness of each one of these plates is 20 millimeters. So 10 millimeters here, 10 millimeters here. ANSA has identified some penetrations, but we know that there is not real penetration. The faces are just too close to each other, but ANSA recognizes as a very little penetration anyways. But we know that this is not a real penetration. Maybe we have a very, very small penetration, but Abaqus is going to deal well with this very small penetration. Okay, we can't have large penetrations, obviously. But in this case, I know that we don't have large penetrations. We're going to have very, very small initial penetration. Even though we have defined these faces parallel to each other and with this distance of 20 millimeters, we are going to have initial very small penetrations anyways, because of numerical errors. So we can just ignore that error, okay? Now let's deactivate draw shell as solid, apply, and okay. By the way, guys, you see that it's not really so practical to go in quality criteria, presentation parameters, and check this box. This is not practical, and I don't do this. I define some shortcuts, such as Ctrl B, is to see the thickness of the plates. I have many kinds of shortcuts defined here in ANSA. I'm not using these in this tutorial. But for example, in the ANSA meshing course, I teach about all these shortcuts. If you'd like to learn how to define it, I can teach you as well. I can create a separate video for it. Or maybe I'm going to teach in the next tutorial so that we can start using it. I don't know. All right, now we can finally output this and run it. So I'm going to copy the path to this folder, and let's save this file and save. And then I'm going to click on File, and then Output and Abaqus. Here we can output the input file to be run in many kinds of solvers. But obviously that I can simply get this module that I created using the Abaqus deck and output a Nastran file. It's going to output the Nastran file, but it's not going to run because we would need to translate this to Nastran here in ANSA. There are some entities that are not compatible, you know? So select Abaqus here, and then I'm going to double click here and Control V the path to the folder, which is this folder here that I have just copied the path. And then I can give a name to this file. So the name here is endplate. You can give any name. The extension is .inp, which is one that is recognized by Abaqus. We can save, and then this appears. Here we can choose the output format version. This is going to depend on the Abaqus version that you're going to run. This doesn't make really so much difference if you're going to run with versions 2016 until 2022, or even more recent versions. This is only important if you're going to run with older versions of Abaqus. You see, in this case, I'm going to run with, I guess, version 23, for Abaqus version 23. But if I choose 22 here, it's not going to be any problem. I'm going to output all, not only what is visible, but all, because maybe I have something that is not visible here, and I want to output it as well. In Filter tab, we can apply some kind of filter to write maybe only nodes, elements, and properties, but I don't want to write any kind of filter. I want to output everything. In comments, these are related to ANSA comments that are going to be written in the .inp file. I suggest to you see that we have this option none. I suggest you to never choose this option if you want to open this .inp file in ANSA again later. Because these comments here are related to the definition of some entities that are internal to, that is only, that's something that is internal to ANSA. For example, the ANSA parts that are here in the model browser is something that is not going to be read by Abaqus. It's not an entity that is recognizable by Abaqus. It's something that is only ANSA can read. So this information is going to be in the ANSA comments, the definition of the parts. But it's important to keep the comments because when we import a .inp file here in ANSA, if you don't have the comments, we are going to have some bugs in this import. Anyways, never select none here. Okay, we can insert the ANSA comments above keyword or at the end of file. So if you don't want to see the comments, just select at the end of file, because it's going to be all placed at the end of the file. And then in here we have the kinds of comments. We don't need to change anything. And in miscellaneous, we don't need to change anything for this module. Okay, so usually what I do is to select all here, and that's all. And then we can click on OK. Now, output completed. If we go to the working folder, here you have the .inp file. Well, I'm going to put this model to run. And then while it's running, we can study this file and how it was written, as we always do for all exercises that we do. So to run this module, we are not going to even open up Abaqus CAE application. If you'd like to open Abaqus CAE application just to see how this module, well, we can do this. Let's firstly run, put this to run, and then we can do all these. So to run it, we need to open up CMD or command prompt application. So search for CMD or command prompt, open this up, and then you see that we are in this folder here. See, users server, I don't know what folder you are, but we need to navigate to this folder where we have the .inp file. So I'm going to copy the path to this folder, Control C, and then to navigate to this folder, I'm going to type cd space, and I'm going to paste the path here, and then press enter. And then you see that now I am in that folder. Another way to do this is, if I close here, I need to right click on this folder, and then actually in my computer I need to right click while holding the shift button, and then I'm going to see these options here, and then I have the open command window here. But I guess this is not something that is standard in Windows. You need to set this up. And to learn how to set this up, you just need to research it on Google. It's easy to find a tutorial. It's easy to do this. Or you can ask ChatGPT. He's probably going to know how to explain to you this. But anyways, if you don't have this option, you can just open up CMD here, CD, and then paste the path to that folder, and then now we are in that folder. Now, next step is to copy the name of this file, select it, and Control C without the .inp extension, and then go back here and then write Abaqus space J equals Control V, the name of that file, space, and then we can have other arguments here. One that I use most of the time is CPUs equals, and then the number of CPUs that I want to use to run this model. So I'm going to run, well, you should know how many CPUs you have in your computer. And then if you don't know, this is another thing that you can search on the internet to learn how to know how many CPUs you have in your computer. And then, well, you can then select how many CPUs you want to use. In my case, I want to use 18 CPUs to run this analysis. This is not a heavy model to run. You don't need to have a supercomputer to run it. But it's going to take quite a long time because of the material, nonlinearity is going to face some difficulties to run. And also because we have applied a pretty large displacement here. Okay, and also there is one thing here that I forgot to do, guys. Now that I've talked about this displacement, I need to define a history output request before I run this module. So I'm going to let this, as you see here, I'm not going to press enter yet. Let's just minimize this. And then I'm going to create, let's get here constraints, double click here, select this coupling. And then from this list, right click, show only, set, new, select node in the database, zoom in here. Looks like we have two nodes in the same position, so we should be really careful. Actually, to be sure that we are selecting the reference node of this coupling, press ESC, close this, and then go to constraint, double click, select this coupling, open this coupling card, and then here we have the reference node of this coupling, double click here, and then copy the ID of this node, close and close, go back to set, right click, new, select node, and then search for this node here, Control V, and press enter. Now we have this node, select, and then middle mouse button, node set, and then this is the disp node where we apply the displacement. Click on OK, go to step manager, and then double click on step 1, output requests, and then in node output, well, we need to create one additional node output. So I'm going to, you see that select node output here, question mark in node set, search for the set that we have created that has ID 23 in my case, and then identifying keys, and I want to calculate translations and rotations, so search for in the letter U, and in the letter R, I want to calculate reaction forces and moments. And click on OK and insert. Now we have this new item, click on OK and close, file, output, Abaqus. And here we are in the folder, here we have the file, I want to overwrite it. So select this, and then you see that we are going to have this name defined, save, here select all, OK, and then select OK in overwrite. Now, this has been updated. You see that it has been saved here at this time. Let me see. 46 minutes. Oh my God. So now in the CMD command, we have this command here that we have prepared. We can press enter, and the job is going to be submitted. So you see, press enter. We don't need to even open up Abaqus CAE. This module is started to run, and now we just need to wait. And when this finishes, we can analyze the files. For example, the .msg file is one of the most important files that we need to analyze. Okay, well, before we start, let's now analyze the .inp file, as we always do. So double click on the, or actually right click on the .inp file and click on edit with Notepad++. By the way, I strongly suggest you to install Notepad++ to read text files. It's going to facilitate a lot. Okay, so if you don't have it installed, then install it and then edit with Notepad++. And then in here we have all the definition of the mathematical module in a way that Abaqus understands. So we have the definition of the nodes. We have this command, node ID, X, Y, and Z coordinates. Anyways, this is something that I have shown to you many times before in the previous exercises, so I'm going to be fast. So we have the definition of element. You see, element type S4 for the quadrilateral elements. Let's see here a definition of material. So here we have the definition of all materials. We have this first one, steel for thickness less than 16. We have the density defined, the elastic properties, so modulus of elasticity and the Poisson's ratio. This is an isotropic material. And then the plastic definition with isotropic hardening, yield strength, 0 plastic strain, and then for 0.1 plastic strain, we have the same level of stress. So this is a perfectly plastic material model. We have the same kind of definition for this other material. And for this one, this is for the bolt. So you see that we have a trilinear curve. Here we have a contact definition. We have only one contact defined, so this is the command that is used. It uses this interaction that has been defined. It is a surface-to-surface contact with a small sliding formulation. Here we have one surface and the other surface of the contact. So this is the slave, this is the master. Guys, before we continue, I know that this module is not going to run. Let me check the .sta file. The .sta file is the status file. Right click and edit with Notepad++, and then you see that we had 4 cutbacks in a row. So what is a cutback? Whenever you see here 1 U or 2 U and etc., this means a cutback. So this means that the software tried to apply as the first increment 0.1, 10% of the total load that we want to apply. In this case, we want to apply a displacement. So it tried to apply, in this case, it wanted to apply the connector load, right, for bolt pretension. So it tried to apply 10% of it. And then it performed 4 equilibrium iterations, which were severe discontinuities. I'm going to talk about what is severe discontinuities shortly. So these are equilibrium iterations. It tried to 4 equilibrium iterations, and it noticed that convergence was not, the chances of convergence was very low. So as a result, it stopped trying, and then it cut back, which means that in the second attempt, it decreased this increment to 2.5%, and then it performed 4 equilibrium iterations, and again it noticed that it was not converging, so we have another cutback. And then it tried with this smaller increment, and then again 4 equilibrium iterations, and again cutback. So it's not going well. When this happens, many cutbacks in a row, this means that it's not going well, and there is something wrong with the model. And the debugging procedure is something that takes time, and for that reason I've already debugged this model, so I know what is wrong, and then we can be fast here to fix it. Let me click in show all. And guys, the file that we should look at when we want to debug a model is the .msg file. So right click on the .msg file and add it with Notepad++. And then this file has been modified by another program. Do you want to reload it? Okay, yes. So here we have the .msg file. And this file is very, very important. And there is so much information in this file that I guess it's not, the best idea is not really to show line by line here. The best idea is to learn what we have here, what we should look at here over time. Okay. And by the way, there is a pretty good application, a free application that you can find on the internet. If you search for this website on the internet, I'm going to write it here. If you type msgfile.info on the internet, you're going to access an application that you can input this file, and there is going to be a report that is going to be generated. I usually use this application to facilitate the reading of this MSG file, but I guess it's a good idea to start looking at this raw file, and then after you learn how to read this file, you can start using applications such as the msgfile.info website. Okay, so In this file, we have some things in the beginning that I'm not going to talk about yet. What I want to talk about in this video is, if we scroll down, here we have increment 1 starts, attempt number 1. And then I have 18 CPUs being used, so the domain is going to be splitted into these 18 cores. And then we have some other information that we're going to discuss later. So what matters here is what we have here, over constraint checks. An over constraint was detected at one of the Lagrange multipliers associated with contact secondary node. And then we have the node ID here. And also we have this node ID associated with this error here. So it's saying there are multiple constraints applied directly or chained constraints that are applied indirectly to this node. Guys, this error is very common. You're going to deal with this error many times. This is not actually an error. It's a warning, and this is what made this happen. This instability in the result. This means that there is two different kinds of constraints applied to the same node. And then this generates an over-constraint issue. And then he says that it is this node here. So I'm going to Control-C. You should do the same in your case. Probably you have a different node ID here. Go back to the ANSA module. And then in here, go to node item in the database, double click. By the way, you should have the Abaqus deck selected here. Double click on node, and then in this search field, Control V the node ID, press enter, select this node, and then you see that the node is positioned here. Zoom in this region, and then you see that it is this node that I have here. And this node is a slave node of this coupling. So the problem here is that this node is part of this coupling, which is one type of constraint. But this node is also part of a surface that we have used to define a contact. Because we have a contact of this green surface, that is the end plate, and this red surface, that is the column flange. Contact and coupling are two different kinds of constraints that were applied to the same node. So I have tested, well, this is an issue that I face for a long time. So this is an issue that I know. And sometimes I commit this error. There are some ways to fix this. The first way is to, instead of using a kinematic coupling, because you see, if I go to constraint, you see, click here, double click here, and then you see that we have a kinematic coupling, which is a rigid coupling. A kinematic coupling generates these constraints that it makes this relative position of these nodes constant. So this is rigid. So this becomes rigid, right? So this is a constraint. Now, if we select distributing, then this coupling is not going to be considered anymore a constraint that has Lagrange multipliers. So we are not going to have this error occurring anymore if we consider this as distributing coupling. But I have tested considering distributing coupling, and there is a very big issue, instability issue. When we have a distributing coupling in a region, there is going to be plasticity occurring. And so the reason why is because the distributing coupling tries to distribute the load uniformly between these nodes, but we are going to have some nodes with plasticity occurring and some nodes without plasticity occurring. And then the stiffness is going to change in a different manner in different regions. And then the coupling tries to distribute the load uniformly, but anyways, there is like a conflict. And well, in the process of debugging, I noticed that, and I needed to perform many tests. And this is an experience that you're going to have at some point when you try to solve a problem. And when you have this kind of issue, you need to try many things until you understand what is the real issue. Because you see, many times, even looking at these files that are generated, we don't have all the information about what is the real issue. Sometimes we need to investigate by performing tests. So just for you to understand how I found it out, I considered the distributing coupling, and I had this convergence issue. And then what I did was I considered the material of this end plate as linear. I just got here the material of the end plate definition, this one. And then I simply set it as no, so I don't have plasticity defined anymore. And then I ran this model without plasticity, and I noticed that it ran without any issues. Okay, so we are not going to consider this option. What we're going to do instead is to adjust the definition of the surfaces of this contact, so that we are going to eliminate these elements from this definition. So let's do this. Guys, in ANSA, there are many ways to do the same thing. I'm going to teach you one way that I usually follow. Let me see how much time we have. Well, not so much time. Okay, so let's search for contact, expand, double click on contact pair, and then we have this contact defined, right? I want to remove from the slave surface, the red one, the elements that are related to these nodes that we have the coupling. So to do this, double click on constraint, create a box selection using the left mouse button to select all these couplings that we have here. And then from this list, right click in one of these items and click on show only. Now here we have the couplings isolated, right? Now I want to show all elements that are connected to these couplings. And to do this, there is this very important tool here, neighbor. Brings to visible all connected entities to the already visible entities. Left click here once. And well, there is one issue because these elements are connected to the underlying faces. And so that it brings all faces visible instead of simply the elements. So we need to do one thing here before. We need to release these elements from this face. And to do this, go to the volume mesh module, which is this module here. Maybe you don't see this option. So firstly, you need to go to this icon, classic mesh module, and then you're going to have this showing up, and then click here. Or maybe, I don't know if you can find it here, I'm not sure. Volume. Yeah, I don't think so, but you need to find it here. And then let's use inside the volumes group the release function. Release shells or solid elements from the underlying geometry. And then create a box selection like this, select everything, and then middle mouse button. And now the elements are not anymore associated with the faces. We can hide the faces. And to do this, you can deselect this option here, macros. Now we don't have any more the faces visible, only the elements. We can click on show all. Now, again, double click on constraints, create a box selection, right click and show only, and then use the neighbor tool. And then you see that we have the elements connected to this coupling showing up. right? These are the elements that I want to eliminate from that contact. Well, to do this, go to set list. You should have the pick tool activated. Left click on this blank space to deselect everything. Zoom in and select this region here of one of these elements. For example, here. We don't select where we have the coupling. Select here. And then when we do this, a set in this list is going to be selected that has this element, which is exactly the set that I want to modify, because this is the set related to the slave surface of that contact. So in this list, end plate surface, right click, modify contents. And then you see that we have 4078 elements. Zoom out, use the right mouse button, create a box selection like this to deselect. And then you see that these elements that were visible were deselected from this set. You know, you see that even though we are deselecting like this, we are just deselecting the elements that are visible. We are not deselecting the other elements. Middle mouse button, you see that now we have less elements in this set. Middle mouse button, and there we have it. Now rotate, left click on this blank space to deselect the other set. Zoom in here, select in the middle of this element, for example. And then we have this set here that we need to modify. Right click, modify content. Use the right mouse button to deselect these elements that are visible. Middle mouse button. And now it's correct. Let's close these. Now let's activate macros here to see the macros or faces. Click on show all. And let's check if this worked. In the contact, double click here and then select this contact. Zoom in. And then you see that we don't have any more of those elements in this contact definition, which means that we are not going to have over-constraint issues with these nodes. Okay, so that's how we fix it, but there is a drawback in doing that, because we are removing this region from the contact definition, but we know that in the physical model, this is a region that we are going to have contact. You know, this region here is one that we are going to have maybe the largest stress in the contact. So that's why this is a drawback. And there is one way to fix this issue, and this is actually related to an article that I have written about bolted connections that is not released yet, but it's about a technique that looks like you see here. Let me see. Okay, I'm almost finished, guys. Before I show this technique, let me just put this analysis to run. So here in Abaqus, after doing this modification, we can go to File, Output, Abaqus, and then select this .inp file, because we are going to overwrite it with the same name here, save, okay, and overwrite. Now in the cmd command, use the up arrow to get this last command, and then press enter to put it to run again using the same command. We have the same name of file, and then here in old job files exist, overwrite, type Y and press enter, because we're going to overwrite the previously created files, these ones. Now it's going to start running again. And let me just show you quickly this strategy that I have used here. You don't need to really do this, but it's just a solution that I found. Instead of creating the coupling on this face, I created another. I created these shell elements that you can imagine that this is representing the face of the washer that we would have here. This represents the face that we would have contact between the washer and the end plate. If I represent here the thickness, you see that this is positioned where we would have contact between the end plate and the washer. Okay? And then I define a contact here, which is this frictional contact. I define a frictional contact here. You see we have a frictional contact. Here I can, with this coefficient of friction, I do the same thing on here. And because, well, now I don't have any more decoupling on these faces, and then because of that I can have this contact between the end plate and the column flange defined considering this whole area. You see, without deleting this area here, which is an important area. Okay, so this is one solution for this problem. But we are not going to do this in this exercise because the solution that we are going to apply to this problem is, well, later we are going to model the bolt, nut, and washer using solid elements. And we are going to define contact and everything. And then when we do this, we are going to solve this issue. So let's think that this model that we are building is not really good to analyze stress in this region. This model is going to be good to analyze the rotation of the end plate connection. So we are going to, for example, generate a curve like this, moment versus rotation, and this behavior is going to be well captured by this modeling strategy. Okay, but again, if we'd like to know, if we'd like to obtain better results of stress around this region, then we need to have a better modeling strategy, such as this one here, which is a pretty good one. Okay, or the using solid elements, which is a computationally heavy. Let me see if the .sta file has been generated. Well, yes, it has been generated. Okay, so you see that now we have applied the first increment of load. You see 10%. We had 21 severe discontinuities, equilibrium iterations, and 2 equilibrium iterations. In total, 23. In the next video, I'm going to talk about what is all this. Okay, we're going to analyze this file in details. Each column that we have here. We are going to analyze the .msg file as well in details. We are going to also continue analyzing the .inp file because we need to finish analyzing it. I started some time ago, but we didn't finish. I'm going to also show you guys how the .inp file is going to look like in the Abaqus CAE application. Okay, anyways, okay, it's almost finishing the first step. In the next video, we're going to continue. Just don't forget to save. And in the next video, then we continue. I hope you like it. I know that this series is getting longer than I was planning, much longer actually. But the reason is because I spend too much time explaining about things that I guess it's important. So anyways, I hope you liked it and see you in the next video.